well, 12:01 p.m., sorry, Central Time. And I am your host, Dr. Matthew Richardson, and welcome to another day of Astro Office Hours, CosmoQuest Astro Office Hours. Um, Give me a quick second. I'm going to go ahead and verify that I'm actually streaming live, which requires Chrome. Oh, what happened? Oh, that's what happened. That was me. My apologies. I got rid of my background image there, which is kind of related to what I'm going to be talking about today. So let's see. Chrome, what do we have? Let's go ahead and navigate to Twitch. Make sure everything's working. It appears. Let's see. All right. Just a little bit of sound feedback there for you guys. It's if you heard what was going on with my browser. But everything appears to be working just fine. But let me go ahead and reset things because that's what it typically takes for me to be able to see everyone's chat. Come on, Twitch. And there we go. I can pop out the chat. All right. So let me quickly make sure the chat is working correctly. So hi all. All right. I can see my comments. If I can see my comments, that means I can be able to see yours. All right. Thanks, Guido. And so let me quickly say hi to everyone who's here. Hi, Guido, and hi, Michael T. Mayer. Hi, guys. Now, there may be more people here, but this is always an issue with Twitch for me that it doesn't show everyone who's currently here. So, but as I said before in my previous streams, if you guys say something to me, I will try my best to make sure I at the very least say hi to you. And then if it's a question, I'll try to answer it. Thanks, Guido. But yes, I saw your previous message. I'm live and in color. Great. All right. So, in my last stream, I talked about, well, I didn't talk about anything that I'm going to talk about today, but I did state that I was going to be talking about equilibrium. And to kind of kick off today's stream, I found this image online. And this is an image of a hotel in China somewhere. But the key thing I want to note here in this image that it kind of like stands out. I mean, things look normal, right? You see at the very bottom of the image, you see cars moving around. Nothing's abnormal about that. Of course, we see some high rises, some buildings. Nothing's abnormal about that. However, as you begin to move to the very top of this image, there's one thing that definitely stands out. And that's this little structure. And let's see if I can kind of like zoom in here. That's this little structure at the very top. All right. I think that's as best as I'm going to get it. That is a swimming pool. That is a swimming pool. And honestly, even if I did know how to swim very, very well, there is no way that I would probably swim in a swimming pool that's kind of just like hovering over the ground like that. I think the caption for this image is like it's up 500 feet. That's insane. However, apparently, our ability, that is mankind's ability to build such structures, has advanced to them now to the point where this is considered safe. I mean, they wouldn't do it, of course, if it wasn't. However, how could we get to this point? You know, with our technology to be able to make structures like this. And that's kind of where today's problem is aimed at. It's going to kind of cover some of the more fundamental ideas behind how we can do such things. And it all is thanks to our understanding of physics and engineering, of course. So let's go ahead and jump into today's problem. I'm going to go ahead and switch scenes. And it's actually kind of showing the image that I want for today's stream, but I'm going to scroll up. And I've just entitled this Physics Equilibrium. I mean, we could talk about all things that, are in a state of equilibrium. So let me quickly make sure that I haven't missed any of the comments. Yes. Oh, that's cool actually. I'm happy to hear someone did a video about it. But yes, I'm gonna be doing a very basic physics problem that kind of touches on the physics behind what's going on with with the pool. I believe the reason why the pool is able to maintain its, or the pool and the building are able to like stay in that particular engineering marvel is that I think they're using what's known as like a cantilever. Hey, Uncle Bill Druin. And so but today, I mean, the physics behind this is related. And so I'm going to go ahead and scroll down. And so the problem is the image below shows a system in equilibrium. The object B has a mass of 0.735 kilograms. Determine the masses of objects A, C, and D. Hi, Larry of the G Cloud. So let me go ahead and make sure I'm not missing anyone else. Hey, Peter. Hey, Tom Van Scotter. And also, there's a new person here. Warp System 1, or Warp System 1 maybe, with the P and R backwards maybe. But welcome. I'm glad to have you here. All right, so this is the image that we're working with. So basically we have a system of basically fishes that are on lines linked to crossbars. And the idea is that the system's in equilibrium, meaning that nothing's in motion. So as we see it, the system's perfectly still. And the idea is to use the mass that we're given for object B, which is some fish, to determine the masses of the other three fish in the drawing. Fishes A, D, and C. All right, so let's go ahead and jump into today's problem. And I'm realizing that I actually might want to make a quick modification to the image to make some of the math make sense. So what I'm going to quickly do, and I'm going to make sure that you guys can see what I'm doing, because it's no fun if I'm just doing stuff and like just talking, you're not actually being able to see what I'm doing. So let's go ahead and make another scene. So duplicate, we'll name this scene 3. And with scene 3, I think what I want to do is just open up, let's see. I'm just going to do this with Paintbrush. I think Paintbrush might be the easiest thing to do. Okay, that's really big for Paintbrush, but that's cool. It'll still work. All right. So let me go ahead and add the Paintbrush window. All right. And let's quickly modify that so you can be able to better see it. So really all I want to do is just simply add some lettering for some of the points in this diagram to make some of the math make sense. All right. So first things first. This point right here, I'm not too sure if you can see my cursor, but what I'm going to do, so I use the airbrush and, all right, you guys can see it, perfect. I'm going to just draw a little point right here. Trying to draw a nice little black point. As this point is important. And we're going to say that this is perfect. And we're going to make a line, and we're going to make this is point E. So right there at the center. And it's going to kind of go through our 5 centimeters, but at the very least, we can probably still, well, let's put it off to the side right here. Let's do this. That, this, and this is point E. I don't think that's a letter that's been used just quite yet. I think the 16 is going to, oh, that's way too small. All right. And I should really move much faster at doing this. Let's do it again. Let's make it bigger. Let's try. That looks about right. Let's do this. There we go. That's a lot better. This is point E. And then lastly, I need one more point right here. Go back to our paintbrush. And so I will say this though, with every physics problem, having a good understanding of your diagram is always important. That's our second point. Go ahead and draw some lines. And this will be point F. And there we have it. I'll go ahead and save that. And so now I can go ahead and update our diagram in 1. So I'll go back to 1 and go back to tech. And if I retech it, it should give us the updated image. All right, there we go. So we have points E and point F labeled now. And hopefully you guys can see that. I can probably make it a little bit bigger. All right, let me check comments to make sure everything's good. God, I promise every time we have these streams, you guys start talking about food and it just makes me hungry. All right, thanks, Uncle Bill Druin. All right, hey, Susie. So let's go ahead and get started with the math for this problem. I can scroll down now, and the very first thing we want to do is we're gonna look at what I'm gonna call crossbar number 1. That's the bar that has the 30 centimeters, well, which in total is 37.5 centimeters in length, where it's been subdivided into 30 centimeters and 7.5 centimeters. And so what we see there is that fish A is attached to the left edge of that crossbar. And at the right edge of that crossbar, we have another system of crossbars. But I'm just going to call that entire system of crossbars system E, because it happens at point E. And we could imagine, though, that that entire system has a mass associated with it, which we're just going to denote as mass, as m sub E, or mass of system E, because that's really what's all important for that top crossbar. For it to be in equilibrium, we have to be able to consider the physics that would be required to understand how it can be in equilibrium. And that physics would be torque. So let's go ahead and put no indent. Using torque, determine conditions of equilibrium. Using torque for the uppermost crossbar, determine conditions for equilibrium. All right. So we'll end up finding, oh wait, this is really small too. Let me make this bigger as well. All right, there we go. All right, so what we'll end up finding is this. In order for them to be in equilibrium, the torque that A produces on that uppermost crossbar must be equal to the torque that's going to be produced by by system E and its equivalent mass associated with it. So what we end up finding is that the torque from object A, or fish A, will end up being basically and using, I should probably also write down what the equation for torque is. So actually, let me go up really quickly and do that. Sorry, guys. I'm just going to do some copying and pasting to make this really fast. So torque, which I'll just denote as T, is equal to, and the mathematical formula for it, the one that's relevant to the problem we're working with, is I think it's R cross F, not F cross R, but R cross F. But the because the nature of our problem, I'm going to simplify it and just basically put it as the product between the gravitational force of whatever mass we have. So so the mass of some object times gravity, G. So we're just going to assume all this stuff is occurring on Earth. It doesn't really matter where it's occurring because we'll end up finding out that the G's cancel out anyway. But m times G, which is the weight of the object, times the physical length that it's out at relative to the point of rotation. And the points of rotation always occur at where the strings intersect our crossbars. So mgr is what I'm going to just basically make this out to be. That's our torque. And so for our first problem, I'll go ahead and typeset this. Okay, it did not like something that I've done here. 31. Oh, because I don't have anything there, that's why. All right, let's just go ahead and just fill in what this information should be. So for our first crossbar, the torque should cancel out, and basically what we'll end up getting is that the mass of object A times the gravitational pull on it times the distance at which it's at. So I'll put r sub a, which we'll understand that to be 30 centimeters, must be equal to the mass of system E times g times the distance at which system E is affecting the torque of that of the first crossbar. Let's just make sure that this is all coming out correctly. So I'm going to scroll down now. There's our torque equation, our simplified torque equation. The more appropriate form is going to be r cross f, which would throw in a sine theta. But like I said, given the nature of our problem, the angle between the r vector essentially and the weight vector from each individual mass in our system is at right angles. So that the sine theta part just becomes 1 for all cases. And also, one thing I forgot to mention is that we are ignoring the mass of the crossbars themselves, because if the crossbars had mass, and we were able to assume that the mass distribution of each crossbar was uniform, then we'd also have to incorporate a much easier terms to add in, accounting for the fact that the crossbars had mass. But in this case, we're going to assume that the mass of the crossbars is either negligible or non-existent. All right. So as we can see here, the torques will end up canceling out. We're strictly talking about the magnitude of the torques. They end up canceling out, and what we end up getting is that, and I'm going to simplify this line here. The G's cancel, and we basically get that the ratio of the mass times the distance relative to the point of rotation are equal to each other for each individual component, that is the object A and system E. Now, this equation actually is very interesting in that it's also related to another concept in physics, and that is the center of mass. Excuse me, the center of mass. And this equation becomes true for the center of mass in the event that the center of mass occurs at the point where the wire that's connected to the uppermost crossbar intersects. So I'm going to quickly take a moment to look at comments. If what I'm saying is not making sense, guys, please let me know. I'm going to try my best to keep referring back to the image. All right. So that's our very first system that we're dealing with. That's the uppermost crossbar. And we're basically going to end up repeating this exact same bit of math for the middle crossbar. So I'll scroll up. For the middle crossbar, as well as the crossbar at the very bottom. All right. And so I'll just copy and paste. So of course, using torque for the middle crossbar, the conditions for equilibrium there would end up being, and I'm going to scroll up so that I can be able to see it, will end up having to be the mass of object, or the mass of system F, times gravity times the distance at which system F is relative to the point of rotation for the middle crossbar. So I'll put that as R sub F, must be equal to the mass of object B times G times the distance at which object B is at relative to the point of rotation for the middle crossbar. And that simplifies to the following. So I mean, the math for this particular problem is actually quite straightforward. However, just kind of relating things back to the initial image that I showed, let's go ahead and change scenes again. Think of a scene 2. So going back to this initial image, the idea here though is that this system is also based off of the idea of being able to be in a state of equilibrium and learning and understanding how torques, right? Understanding how the torque on this little the pool that's actually sticking out, assuming it to be like a crossbar with mass, of how it can remain in a state of equilibrium. And so the math for that, you could break it down to being a bunch of sticks and stuff like that, but it's going to be of course far more complicated because they have to make sure that it's completely safe for people to be able to swim in. But you can always make a kind of like a stick diagram of it and work through the math for it. But in this case, I'm just choosing a much more simpler idea or scenario to work with. Don't look mad. Oh man. Yes, Peter is teasing me. Because I always get hungry during these streams. And I mean, of course it is lunchtime for me, but like you guys are always eating. I mean, risotto? Really? Oh man. Ah. All right, let me get back to the problem. All right, so we've done the math so far for crossbar for the middle crossbar, and we're basically going to repeat the exact same thing for the very last crossbar. All right, so I want to go ahead and say using torque for bottom crossbar. And so for that system, we actually have, masses at both ends of the bar. And so we have the mass of object D, we have the distance at which it's out at relative to the point of rotation for the bottom crossbar, and we have the mass of object C and its distance. And again, it all reduces to being, because the gravitational pull on these objects cancel out, and it all reduces to just being having units of mass times length. And so, I mean, for the most part, whenever I work any problem, and I mean, it's always a good idea to do this, is to ensure that you work strictly with variables and try to avoid throwing in numbers because it's quite easy to make a mistake with the numbers, and then that mistake, of course, will propagate to the rest of the problem. Whereas, of course, variables make it more general. You get a general result, and you can always plug in numbers at the end. So I'll go ahead and typeset this. And there we have it. I think I have all the conditions that are important here. All right, so now we're going to go ahead and start making our relationships. So scrolling back up here, we are actually given the mass of object B, and of course we're giving all the various values for our R variables. And so, and for this problem, I'm actually doing it without notes. Like I said, I found it I found the problem in our last stream. So I'm thinking through this problem as we work through it. So the very first thing we probably want to do is probably make a relationship between mass F and the information that we have related to that. Yeah, let's go ahead and do that, actually. Yeah, let's go ahead and do that. That makes it, that's actually an easy thing to really quickly do. So I'll go ahead and put no indent. Determine the mass of system F. Mass of system F. And again, I'm going to do this such that we're going to keep it still in variable form. All right, so, and this is actually very easy to do. I'm just going to copy and paste what I have up here. The mass of system F is basically going to be the mass of mass of object B times the ratio. So fraction, the ratio of the distance out to which B is relative to its point of rotation. Object B is relative to this point of rotation, divided by the distance at which mass F is at relative to its point of rotation. For, I believe this is the second crossbar. All right. All right, so as of right now, we know what mass F is. And mass F will, of course, have a real physical value because we know the exact values for mass B, R sub B, and R sub F. So I'm going to go back up to our image here so I can kind of get an idea of where to go from here. Okay. And so mass F, which is going to be the total mass for system F, of course, is going to have to be the sum of all the masses in that system. And because we're ignoring the mass of the crossbar, mass F has to be related to the sum of masses D of object D and object C. So I'm also going to write on the same line, this must be equal to M underscore D plus M underscore C. And I will typeset that. And so that's what we end up getting for this. All right, this is good so far. We can reduce this equation. Actually, let me put this on another line. No, I'll leave it like this. I like it like this. And I should have put determine the system of mass. Determine the mass system F. Sorry about that. Let me quickly check comments because I typically just get into just talking and thinking through the problem. I'm not actually looking at comments. Buffalo mac and cheese. Guys, you're killing me, guys. You're killing me. Oh, mandarin oranges are like a good, like dessert with all of that. All right. So we can actually we can choose either mass D or mass C, and we can use the set of equations I'm showing here in the middle of the screen. Let's make sure the middle of the screen is the same for you as it is for me. We can actually go ahead and solve for either mass D or mass C using the relationship that we see here, where we have mass D times R sub D is equal to mass C times R sub C. So what I'm going to go ahead and do is I'm going to solve. I'm going to go ahead and solve for mass. Let's go ahead and solve for mass D. It doesn't really matter which mass we choose, but let's go ahead and solve for mass D. So I'm going to put, again, copying and pasting is always my friend because that makes things go faster. So determine the mass of D, of object D. And what we end up getting is that the mass of object D is equal to the mass of object C times the ratio of R sub C divided by R sub D. I can go ahead and typeset that. I think so far so good. And what this actually allows me to do is now determine an equation where I can actually find out what the mass of object C is. So I'm going to go ahead and put determine and so what you'll notice with these problems is that when you're working through them, mathematically speaking, this problem isn't so difficult. But it's very tedious, right? A lot of steps are involved with it. So determine the mass of object C. I'm going to put M sub C. We know that M sub C is going to be equal to, or better yet, I'm going to go ahead and use this equation up here. I'll just copy and paste it because it makes it faster doing it like this. Oops, pressed the wrong button there. Copy and paste. And I'm going to move everything such that it's still mathematically correct. I just want things to be kind of restructured here. And so we're going to end up putting that M sub C is equal to M sub B times that ratio of distances minus M sub D. And get rid of this plus sign. And I think that this should be just fine so far. All right. So this is where we're at. But we also know what M sub D is equal to, right? M sub D I'm looking at this and I'm realizing that it might have been a lot easier if I would have left the M sub D over there. So I'm going to do that actually. I'm going to move the M sub D back over. How was it before? Okay. It's going to make the math a lot more easy to look at. And I would have to move some things back over to the left-hand side anyway. So let's go ahead and put the plus sign back. Let's go ahead and go with this relationship that we had determined earlier. And we're going to substitute in for M sub D the fact that it equals to M sub C divided by times that ratio of R sub C over R sub D. Copy, make the substitution. All right. I see that I'm time is always running against me. So I'm going to go quickly with this. All right, we can factor out the M sub C on the left-hand side of the equation. And I see left, right, that the final form of that will be a ratio, a fraction, all right. It's going to be R sub C plus R sub, R sub C plus R sub D divided by R sub D. In this situation, I've kind of skipped a line or maybe one step. But if it's not clear what I've done, I'm more than welcome. I'm more than happy to answer questions, of course. And of course, this is still equal to the same thing on the right-hand side of the equation. All right, good so far. And then finally, to isolate M sub C, we can go ahead and we can divide out that ratio of R sub C plus R sub D divided by R sub D. And all that does is add a factor of the reciprocal on the right-hand side of the equation. So I'm just going to go ahead and do that. Cut, paste. think all that matters is the order of these things, so I can cut that, I can paste it there. I think that that should work. All right. So far, so good. So, at this current moment in time, we know the exact value as far as numerically speaking. Well, not numerically, but as far as an actual physical value is concerned, we know the exact value of the mass of C because all the variables on the right-hand side of the equation that we're seeing here, we know the values of. And because now we know the exact mass of C, we know the exact mass of D, given this relationship right here. All right, so I think the very last thing we have to do is figure out what is the mass of A. So going back to our drawing, we know that the mass of A, or its torque, the torque that's going to be produced by object A, has to be equal to the torque that's produced by system E. Do we know the mass of system E? Well, the mass of system E is going to basically be equal to the sum of masses of that system, which are basically just objects B, C, and D, which we now know the physical values for. All right. So So we need to figure out what the mass of system E is in total. And so I'm going to go ahead and write that out. Again, we're going to copy and paste to make this go by fast. To determine the mass of system E, and so I'm going to go ahead and write here. And you know what? I feel like I've been talking for quite some time now, and I've been neglecting to look at the chat. Okay, so guys, if can you guys still see and hear me by any chance? I just want to make sure that I haven't had any issues with the stream. The very last message I'm seeing right now is it's all good. Let me go ahead and check. Okay, we're speechless. Hopefully, we're speechless is a good thing. As in, like, oh, Matt, we know this. We don't have any comments or any questions. Okay. All right, so let's go ahead and continue with this problem. So mass of system E has to be basically equal to the sum of mass of, and I'm going to scroll up actually so I can see the image while I do this. The mass of system E has to be equal to the sum of objects B, D, and C, their individual masses, respectively. All right, so B plus, and it makes it easier if I just copy and paste. B, we get D and C. All right. I can go ahead and plug in what I know for these masses. For the mass of B, and I'll just scroll up here. Oh wait, mass of B is already given. So I could just put m sub B. I'll leave it as that. The mass for D You know what? Let's just go ahead and solve for actual physical values for these, now that I'm thinking about this. So I'm actually going to kind of go back a little bit. And we're going to go ahead and first go ahead and just put in the physical value for m sub C. All right, so m sub B was given to us. I'm going to scroll up here. And its mass was 0.735 kilograms. We'll just, of course, work with that unit. 0.735. I think it's that. That works. kg. And this is going to be times those really long fractions as far as my tech editor is looking. So I can copy and paste this actually. I'm very tempted to just kind of like just drop this unit in here and realize that the total unit comes to be kilograms anyway. In fact, I think I'm going to do that. That's just going to make things easier for me in the long run. Just note that the mass is going to have to be in kilograms. All right, so, and of course, the units for the unit for length is also going to be the same. Anyway, they all cancel out because I'm taking ratios of the lengths. All right, so R sub B is going to be 5, and we just understand that it has the units of centimeters, but the unit of length with the entire problems I'm working is the same, so I don't have to really be concerned with adding them in the fractions. Even though if you want to be good with doing the math, you should always add the units. But given the time, I want to go ahead and just quickly get through it. So the distance for F. Oh, sorry, 15 centimeters. Or 15. It's like, what is that? What did I do there? All right. Distance for D is 17.5. This is the reason why it's good to have a good diagram and making sure you understand what things are in your diagram. The distance for C is going to be 5. The distance for D is going to be 17.5. All right, I can go ahead and typeset this. I'm actually going to scroll down to where I'm actually having numbers show up. Let's go ahead and fix that formatting. All right, Matt, 10 minutes. We can do it. All right, so M sub C is equal to, and I'm going to go ahead and get my calculator out and hopefully not make a mistake. So 0.735 times the ratio of 5 divided by 15, which is a third, I believe, right? A third. But I'm going to let my calculator do the calculating for me. So 5 over 15 times that very last thing, which is going to be 17.5 divided by 5 plus 17.5. And I know you guys can't see what I'm doing here, but I'm using my max calculator to figure this out. And it's roughly like 0.19. I'm just going to do that. 0.19 is the solution I end up getting, which is almost approximately equals to 0.2. And I might end up rounding to make things easier, but 0.19 kilograms. And we can check the math and make sure it conceptually it makes sense, right? Because a good analogy for this is if you think of like kids on seesaw, two kids on a seesaw, right? So all right, so that's M sub C. Let's go ahead and do M sub D now. So I'm going to go ahead and let's put back to determining the mass of object D. So we know M sub C is going to be the 0.19 kilograms. And again, we know our final unit's going to be in kilograms. So how did I do that before? All right, cool. I'll keep that and just make a new line. M sub C is going to be 0.19. We know the unit's kilograms, so we don't have to worry about adding it at the current moment. We have a fraction here. It's going to be r sub c, which I need to go back to my diagram again because I'm doing very poorly with like trying to remember these numbers for the lengths. R sub c is 5, and r sub d is going to be 17.5. And so what we should get for this is 0.19 times the ratio of 5 divided by 17.5. Which is kind of almost like 0.05. I'm just going to go out to two decimal places for each of these numbers. That's good enough. And this has to be in units of kilograms. I think this should be good. Let's go ahead and scroll down and make sure all the math is coming out properly. All right, so far so good. M sub C, M sub D, we have those. Now that we have those masses, we can figure out what the total mass of system E is. So the total mass of system E has to be the mass of B, which we were given as 0.735. Added onto that is going to be the mass of D, which is 0.05. Well, actually, I'm seeing now that the mass of D is, the mass of B is out to 3 decimal places. So I probably should have kept that. Oh, man. All right, well, it's all right. I probably should have kept that. I'm pretty sure I should have kept that now. I'm trying to think back to my days of when we were discussing in physics class propagation of uncertainty and stuff like that. But oh, it's been a while. So M sub D, so 0.05 and 0.19 for M sub C. And so that comes out to equaling, this has to be in units of kilograms. And this problem is almost done. And as you kind of note here, like most of the problem now is just simply arithmetic. All right, so 0.975. And of course, that value has been thrown off. Probably not significantly, but thrown off because of the fact that I've done rounding. So 0.975, which is almost close to a kilogram. So the mass of system E is almost close to a kilogram. Unfortunately, I don't think in units of kilograms, so I don't really know how massive that is, to be very honest. In fact, I don't think many people in the U.S. think of in terms of kilograms. So typically, when we think of mass, we don't really think of mass. We think of weight. You'd sell someone so many pounds of something, but to actually get the true mass, you'd have to divide that by Earth's gravity constant, and then get that into its proper units as well, though. So, but M sub E is that. And so now we can actually figure out what the mass of object A is. So I'm going to go back up here. Actually, I'm just going to copy and paste some stuff because it makes it easier for me. We got 4 minutes left. I'm going to do this. So determine the mass of object A. And we know the mass of object A. It's basically going to be equal to the mass of A times the mass of system E divided by R sub E, times R sub E divided by R sub A, right? And so to kind of finish off this problem now, we're going to get mass of A is equal to 0.975 times the ratio of R sub E, where R sub E is 7.5, divided by R sub A, which is 30. And what we finally get is our answer for the mass of system A. And hopefully I have some time to quickly talk about how we know this stuff makes sense. 0.975, this is going to be times 7.5 divided by 30. We get 0.24, and I'm just going to keep up with, 2 decimal places. I should be far more exact than that, but I mean, I'm not going to worry too much about it. There are rounding errors, of course, in this final solution, but the main point is being able to understand how to work such a problem, because the way in which we work this problem is kind of similar for how structural engineers would have to approach their problem. Of course, there's going to be a whole lot more math involved, a whole lot more things to consider, because in their case, whatever crossbars they have to consider the mass of those crossbars. Whatever sort of physical lines they have attaching to the crossbars, or ropes or anything, they have to consider the tension in those ropes. So, of course, our problem is far more simplified, but still, nevertheless, the physics that's involved is similar, if not the same. But yeah, final mass of A is going to be 0.24 kilograms. And the way in which you think about this, to make sure things make sense, let's take, for example, crossbar A. Let me look at the comments to make sure I'm not missing any key comments here. So the way in which you think about it is that for crossbar number 1, we now know that the mass of system E is about 1 kilogram, and the mass of A is much less, right? And that makes sense because of the idea of torque. Going back up top, so I'm going to scroll down a little bit here. Going to this concept here of torque, or this equation here for torque, we have mg times r. And really, because the g's cancel out, you're really looking at the products between m and r. You're trying to find the product of the mass of A times its distance it is relative to its point of rotation for crossbar, the upper crossbar, compared to the mass of system E times the distance it's out relative to its distance relative to its point of rotation for crossbar, the upper crossbar. And given that the distance to system E is smaller than the distance to object A, you'd expect for the mass of object E to be much greater than, or at the very least greater than, the mass of object A. And you kind of have this kind of idea that the products have to equal to each other on both sides of the equation. And so the masses that I'm seeing here for system E relative to object A makes sense, or at the very least, it's what's the word I'm looking for? It makes sense. I can't think of the word I'm actually looking for, but it makes perfect sense that the mass of system E is much greater than the mass of object A. And you can keep doing this whole line of logic, this exact same type of logic for the middle crossbar and for the bottom crossbar as well. All right, guys. I hope you enjoyed today's stream. I realized that I didn't get to look at chat as much as I would have wanted. But I do want to say one thing about my last stream. Oh, cool. So, so Uncle Bill Druin, did my math make sense? And did my explanation make sense? That's the I guess that's the key thing. I'm just so happy with our community. Actually, I mean, we have a bunch of people who have a lot of expertise in like a wide range of fields, and it's amazing. But yeah, I wanted to make a quick comment about my last stream, um, and there was some questions about, if I'm remembering correctly, about if you have light going through a potential, how does that affect the redshift? And so I think the idea of what you guys were saying makes perfect sense, right? As the light goes by this particular region that has some high gravitational potential, the idea is when it enters, of course, the light would, I would assume, would be blue shifted, but as it exits that system, it would end up getting red shifted, ultimately making the point where those effects kind of cancel each other out. And so if you do have a system where, or a situation where light has been gravitationally lensed by some massive object, you'd expect for the net result for the red shifting to be negligible, to the point where it can just be ignored. That is, the initial frequency at which the light started off with will more than likely be the same frequency that's going to be observed by an observer, given the situation that we were talking about. I realized that I didn't quite answer that question or even talk too much about it. But guys, I hope you guys enjoyed today's stream. If I'm not mistaken, Astronomy Cast is going to be in like an hour's time from now. Um, and I'm not too sure, but Joe might be on tonight. I think I may have heard that he's going to be taking over for Pamela on Sunday. So maybe he's not going to be on tonight, and maybe he's going to be on just Sunday. Is that correct, Susie? I know that Susie's here, or I hope she's still here. If not, you will be updated. All right, guys. Well, thanks for joining today's stream, having some fun talking about this particular equilibrium problem that I found in my physics book. Um, if you guys have anything you want me to like talk about, in particular, I will definitely see if I can find a problem that's related to it, and we can just work through the problem. All right, guys. Oh, Astronomy Cast was done yesterday. Ah, okay, that makes sense. All right. Well, then that means I can go watch it now, probably while I eat some food. Um, okay. All right. That's what I thought I read somewhere on the Weekly Space Hangout Crew Slack. Oh yeah, that's right. For any of you guys here, and I'm not too sure of all who's here because at times when I go to check who's physically in the chat room, things somehow get weird with my particular chat. But for all those who are here and aren't a part of the Weekly Space Hangout crew, I recommend that you guys go check them out. They're cool people, and as I said earlier, they're like experts in a lot of different fields. Um, and so, guys, again, thanks for joining. I will see you guys next week. All right, bye.